In this section, we'll introduce the attention mechanism, a fundamental algorithm that powers advanced models like GPT. Here, it's adapted to handle images instead of text and integrated into the YOLO architecture. As always, we'll begin by setting up the stage in our Colab environment. This block corresponds to stage 10 and uses the following initial parameters during initialization: 256 for C1 input channels, 256 for C2 output channels, and 1 for the number of loops. Additionally, the expansion factor is set to 0.5, which creates an intermediate variable C with a value of 128. Both CV1 and CV2 are pointwise convolutions, maintaining the same number of input and output channels. During the forward pass, the process starts with CV1, and the resulting output is split into two tensors, A and B. Tensor B is then passed into M, which is a sequential PSA block configured with one loop, as specified by the initialization argument N. Now let's dive into the PSA block class. During initialization, this class defines three components: the attention mechanism, a feed-forward layer, and a shortcut. In the forward pass of the class, we enter the attention block, add a skip connection, pass the result through the feed-forward layer, and add another skip connection before returning X as the output of the C2PSA block. To better understand this process, we can print out intermediate steps here. However, let's move on to the visualization portion to solidify this flow further. We start with the input tensor, which originates from the SPPF block. Next, we enter the C2PSA block, beginning with CV1. This is a one-by-one convolution operation that keeps the tensor shape unchanged. After CV1, the tensor is split into two halves along the channel dimension. The first half, A, is stored for later use, while the second half, B, is passed as input to the PSA block, starting with the attention block. Within the attention block, the tensor B undergoes several operations, including query, key, and value generation. We'll dive into the specifics of this process shortly. The output of the attention mechanism is combined with a skip connection, and we then move into the feed-forward network. In the feed-forward network, the tensor is processed by two convolution layers. The first one increases the channels to 256, while the second convolution reduces the channels back to 128. To this result, we add another skip connection for improved information flow. Returning to the PSA block, we now concatenate the earlier stored tensor A with the processed tensor B. Finally, we apply CV2, another one-by-one convolution operation, which preserves the tensor shape. This marks the end of the C2PSA module, with the output tensor shape matching the input. Let's run the code now. We'll begin by jumping into the convolution class to perform the CV1 operation, returning its result to split the tensor into A and B. As we mentioned earlier, B will then be fed into the PSA block. At this stage, we're essentially entering the attention mechanism. So let's take a moment to explore it in more depth. Given the importance and relevance of this algorithm, I've created a dedicated section to dive deeper into the world of attention mechanisms. As many of you may already know, this is the conventional attention mechanism introduced in the original transformer paper. It is widely used in transformer-based models, with its operations progressing from higher to lower levels, moving from left to right, as illustrated here. However, we won't spend much time on this standard implementation, as there are already plenty of excellent explanations available online. Instead, we'll focus on the YOLO implementation variant. In YOLO11, an alternative approach to the attention mechanism is introduced. If this looks intimidating at first glance, don't worry, I'll walk you through it step by step. By the end of this section, I hope you come to appreciate its elegance and practicality. This implementation diagram was created based on the only source of truth available, the Ultralytics code. I've included a link below for your reference. To start understanding what this all means, let's begin at the very start with our input tensor to the attention block, which has the shape of 1 by 128 by 15 by 20. To build some intuition about what this tensor contains, here you can see its corresponding feature maps. I'm showing all 128 channels here, grouped into 4 blocks of 32, so we can visualize them more clearly. Now, what do these feature maps actually represent? As you may have already guessed, each of the 128 channels represents a unique feature map capturing distinct properties of the input data. These features have been learned by earlier convolutional layers or operations before reaching the attention mechanism. Let's break this down. These feature maps capture diverse information, including edges, boundaries within the input, textures, surface details or patterns, shapes, geometric structures formed by edges and textures, patterns, meaningful regions formed by shapes and textures, and object parts for specific components like wheels or faces. Together, the 128 channels create a detailed representation of the input's context, each pixel containing local context, information from its immediate surroundings, as well as global context, insights from earlier layers, showing its role in larger patterns. This rich combination provides a strong foundation for the attention mechanism to analyze spatial and feature relationships effectively, enabling meaningful and context-aware processing in the next steps. With that foundation in place, let's return to our input tensor. The first operation we perform is a pointwise convolution to obtain a new tensor named QKV. There is no activation in this layer. Instead, the inputs are linearly mapped to the output, which has twice the number of channels. In essence, we've applied a linear convolution to produce the QKV tensor. Another way to think about this is that the 128 input channels have been projected into a 256-dimensional space. This transformation allows the model to learn a new representation of the input features while preserving the spatial structure of the data. Now, let's shift this tensor to the left and break it down. The reason for doubling the size is that the attention mechanism uses two heads. This results in a total of 64 queries, 64 keys, and 128 values, as you can see here. Each set of Q, K, and V corresponds to a specific attention head. To better understand the content of these Q, K, and V tensors, let's first take a look at head 1. Notice the similarity between the query and key feature maps. This property will become critical shortly, and we observe the same trend with the values. Next, let's look at the Q, K, and V tensors for head 2. Again, we see the 32 queries. By the way, notice the uniform bottom left feature map? I was curious and took a closer look at it. This may suggest that this particular feature map has essentially frozen and is no longer contributing, possibly indicating a dead neuron. It could be the result of saturation or a quirk in the initialization or training dynamics. The remaining feature maps appear to be healthy and show expected variability. Moving on, here we see the 32 keys and the 64 values. First the first 32, then the second 32. Now, instead of separating the tensor by head, we can reshape it as follows. We unpack the number of heads and combine the height and width into a single dimension. This results in each Q, K, and V tensor corresponding to both heads and for the 300 pixels. To better visualize this, you can think of it in a 2D representation. Focusing on one head at a time, we can see how the reshaped tensors look for the queries, keys, and values. For those curious, each row in these tensors represents a feature map 15 by 20 that has been flattened. The 300 columns correspond to the spatial grid. For each pixel, the 32 channels form a feature vector that represents the queries associated with that pixel. We can see the values corresponding to the 32 queries for pixel 1. Another way to interpret this is by looking at the top left pixel. This pixel's values in the first feature map correspond to pixel 1, but since it's represented across 32 features, all 32 values form its feature vector. Using the same approach, we can quickly show the 2D tensors for head 2. Now that we have our queries, keys, and values, we're ready to introduce the attention formula that ties them together. Understanding this formula is essential to grasping the code. The standard formula follows the scaled dot product attention mechanism. Here's how it works. The query is multiplied by the transpose of the key. The result is scaled by the dimension of the key vectors. It's then passed through a Softmax function to compute attention weights. These weights are applied to the values to produce the final output. This approach is foundational to many state-of-the-art models, like GPT. However, YOLO11 introduces a variation of this attention mechanism. While it retains the core principles of scaled dot product attention, it changes the order of operations. The transpose of the query is multiplied by the key first. After applying Softmax, the result is transposed before being multiplied by the values. Although mathematically similar to the standard method, this variation may be optimized for vision tasks or specific requirements within the YOLO architecture, such as improving computational efficiency or simplifying implementation. This distinction is crucial for understanding the code. Let's now use our queries, keys, and values to perform what's called scaled dot product attention. The steps are outlined to the right. Let's walk through them. First, we transpose the queries to a 300 by 32 shape to enable matrix multiplication. Notice that the queries are arranged top to bottom, with each query containing its 32 features. Queries represent the specific features the model is trying to focus on, like edges, textures, or objects. Keys represent potential regions or parts of the image that might contain relevant information for those features. When we compute the dot product or matrix multiplication between the queries and keys, the result is the attention matrix, which captures the similarity between them. You can think of attention weights as a measure of how relevant each key is to a given query. Here's an intuitive example. Pixel 1 query asks, "This is what I'm looking for." Pixel 2 key responds, "This is what I have to offer." The dot product between Pixel 1 and Pixel 2 determines how much attention Pixel 1 should give to Pixel 2. A high attention weight indicates that the key's information is highly relevant to the query. This process is repeated for all other pixels, Pixel 3, Pixel 4, and so on. Essentially, every pixel compares itself to every other pixel in the grid. This means that each pixel, whether near or far, can attend to any other pixel in the 15 by 20 grid. This is one of the main powers of the attention mechanism. Every pixel gains global context by understanding the content of all other pixels. Here you can see the resulting 300 by 300 attention weights for both head 1 and head 2. However, we cannot interpret the attention weights as they are because they are not normalized. Without normalization, the attention weights lack a clear relative meaning, making it difficult to determine how much importance each key contributes to a given query. That's where the Softmax function comes in. Softmax transforms the unnormalized attention weights into a probability distribution, ensuring the weights for all keys sum to 1. This makes the weights interpretable, representing the relative importance of each key to its corresponding query. In most attention mechanisms, the standard interpretation focuses on how all the keys attend to each query. This query to keys perspective is shown here on the right. However, in the YOLO11 implementation, the attention weights matrix is transposed, as shown on the left. This change provides a new perspective by effectively reversing the relationship. It shifts the focus to understanding how each query interacts with and weighs the importance of the keys. Here, you can see the normalized attention weights both before and after transposing the matrix. Now, let's take a closer look at head 1. For example, we can examine how query 1 attends to all 300 keys. The same analysis can be done for query 2, query 3, and so on. If we plot each of these vertical slices, one query at a time, for their associated 300 keys, we begin to see how each query weighs the importance of different keys. These keys correspond to the 15 by 20 grid. Keep in mind that queries often assign a high weight to their corresponding key, as you can see here. This behavior, known as self-focus or diagonal dominance, arises because the self-attention mechanism is designed to allow each query to prioritize its own key. This helps the model focus on specific local features while still attending to other parts of the image, enabling both local and global feature aggregation. Once again, we're observing how a specific query interacts with all 300 keys. Now, this is where things get interesting. Notice how queries corresponding to the car pixels interact more strongly with keys in the surrounding area. This interaction highlights the contour of the car, almost as if the attention mechanism is recognizing and prioritizing the object within the image. This behavior illustrates how self-attention effectively captures spatial relationships, allowing the model to focus on the most relevant features for a given query. It learns to identify and emphasize critical structures, such as edges and object boundaries, which are essential for object detection. We can complete the visualization by examining all the way up to query 300. By the way, I've included the code to generate these plots in the Colab notebook, so you can reproduce them yourself if you're interested. With that, we can now move on to exploring the values in the attention mechanism. Remember those 64 by 300 values we saw earlier? We'll need them again now, and we can quickly visualize them here again for both heads. In the attention mechanism, the values V represent the actual content or visual information that will be passed along after the attention weights are computed. These values contain the relevant features from the input data, which the model uses to make informed decisions. The attention weights we calculated earlier are used to compute a weighted sum of these values. Therefore, the attention output is the weighted sum of the values, based on the similarity between the queries and keys. As a result, we get a 64 by 300 matrix. While we've been working with a single attention head for simplicity, remember that these operations are actually performed for 2 attention heads. This means we need to account for both head dimensions in the full shape. Now that we've completed the attention mechanism formula, we can visualize these results. However, there's not much insight to be gained from this visualization alone. While we've already used the value matrix, we're going to leverage it again, but this time for a different purpose, calculating something called a positional encoding. So let's retrieve that V tensor once more, and this time we'll use it to generate a positional encoding. Let's dive into what that is and why we need it. In attention-based architectures for images, like YOLO11 or vision transformers, positional encodings play a critical role in introducing spatial awareness to the feature maps. Why is the value matrix used as input for positional encoding? The V matrix is ideal for this because it already contains rich contextualized features of the image, making it well suited for encoding spatial information. Unlike the query and key matrices, which help define what to attend to, V is more closely tied to the image's spatial structure. As the actual content of the image, it's better suited for integrating positional encodings directly. So what we'll do next is use the V tensor as the input to a depth-wise convolution layer. The depth-wise convolution ensures that each of the 128 input channels is processed by its own filter, capturing localized spatial patterns within each channel without blending information across channels. After the depth-wise convolution, the identity layer performs no mathematical transformation. It simply passes the output of the convolution unchanged, serving as a placeholder to maintain modularity within the convolution class. The result is a positional encoding tensor with the same dimensions as V, but it provides additional context about where each feature is located within the grid. Next, we'll focus on the concat layer in the multi-head attention diagram. Remember, our attention tensor has dimensions 1 by 2 by 64 by 300. When we combine the 64 attention values for both heads, it's equivalent to concatenating them. We also reshape the 300 into a 15 by 20 grid, maintaining the structure that captures how features across the grid relate to one another. When we perform the element-wise addition of the attention tensor and the positional encoding, we obtain a new tensor. This tensor enhances the model's ability to reason not only about what the features represent, but also about where they are located, allowing for more spatially informed decisions. Let's move it to the left here. So, are we done yet? Almost? While we could use the attention with positional encoding tensor as the final output of the attention class, this approach has limitations. Without a final linear layer, the model might struggle to fine-tune features, miss important feature interactions, and underperform due to a lack of adaptability. To address this, the tensor typically undergoes one last point-wise convolution. This linear projection maintains the same tensor shape while refining the feature representation. We can see the 128th feature maps here, displayed in 32 chunks. These feature maps encapsulate both the representation and the spatial relationships of the attention block. This marks the end of the multi-head attention section. Now that we've covered the concepts and steps involved, I encourage you to explore them further in the Colab notebook. you can interact with the different operations and tensors for a deeper understanding. Let's also return to VS Code and run this section. As we've discussed, the process begins by running the input X through the QKV convolutional layer, which returns a combined QKV tensor. Next, we reshape and split the tensor along the channel dimension to extract the query, key, and value matrices in the correct format. Then we compute the attention weights using the scaled dot product formula, followed by a softmax and transposition. These weights are used to calculate the weighted sum of V, after which we add the positional encoding. We'll then jump to the convolution class for the positional encoding. The result of this step undergoes another convolution to project it back into the original shape, completing the attention block's processing. Finally, we return this output to the PSA block. With the attention class section complete, we're ready to move on to the skip connection and the feed-forward network. Let's dive in. We will first add the skip connection to the result of the attention block. Next, we apply the sequential feed-forward network. This network consists of two pointwise convolutions. It refines the feature representation by expanding the channel dimensions from 128 to 256 and then projecting them back to 128 channels. Notice the double convolution step here. This temporary use of a higher dimensional space enhances the model's ability to learn richer patterns, complementing the attention mechanism and ensuring the features are effectively transformed and aligned for the next stage. The result is then summed with the skip connection. Next, the result X is returned to the C2PSA block. Inside this block, we overwrite the previous values of B with the result of the PSA block. We then concatenate the original unprocessed features A with the updated features B along the channel dimension. Finally, the combined result is processed through the CV2 layer, which refines the feature representation, ensuring the model can effectively leverage both the raw and transformed features to improve predictions.